A very good afternoon, dear colleagues. I am Dr. Om Pradyum Gupta. Today, I'll talk about quantum computing, its concepts, foundational technical stacks, applications, and use case. Before I start, I would like to discuss about the misconceptions. We all think that it is a faster PC, but it is not just a faster PC. It is different paradigm altogether. It cannot run standard Windows and Office applications. So for these, we need to have different set of applications and tool sets. And till today, it has not broken all the encryption. And we think that it can be available on every desk, but for near future, it is not possible because it needs extremely cooling condition, near to absolute zero. So quantum computing is a specialized set of technology, branch of technology, which leverages the fundamentals of quantum physics to solve highly complex problems, that too in exponentially faster pace. So at a glance, we'd see what is the classical and what is the quantum. Classical uses bit 0 and 1, but here in quantum, we use qubits, which is 0, 1, or both. Processing is sequential and parallel in classical, but in quantum, we have quantum parallel mechanism for processing. So at a time, multiple set of information can be processed. Classical is best for everyday tasks, but for optimization and simulation problems, quantum computing is used. Here in classical, we have very low error rate, but the quantum is prone to higher error. Temperature is room temperature in which classical computer works, but for quantum, we have to have very low temperature. Status is very widespread, but quantum is under research. So here I would like to mention the name of Feynman, who is a Nobel laureate for quantum electrodynamics. In 1964, he has given a remarks about the quantum mechanics, which was, I think I can safely say that nobody understands quantum mechanics. So that created a hue and cries in the world of physics, in the group of researchers, physics researchers, and that was the starting point, which takes us to today's where the quantum mechanics is. Quantum mechanics is, yes. So in 1982, he had proposed how the machines can be created using the law of quantum mechanics instead of law of classical physics. After 3 years, David Deutsch, using the classical Turing machine, he had devised quantum Turing machine, and he has also given the quantum circuits, which are universal for quantum computing. In 1994, Peter Shor came up with quantum algorithm to factor very large numbers, in that too in polynomial times. And Love Grove, that he has devised an algorithm which is really useful for our surging algorithm. So this is again the differences. We have discussed about the bit, then logic gates. Here we have AND, NOT, or gate, but here in quantum we have different set of gates. I'll discuss in later slides. Storage, hard drives and RAM we use, but quantum states are being used to have stored all these large data sets. Gigahertz processors are used, but in quantum we have different mechanism to measure the speed. For word processing, daily work, accounting, etc., classical computing is ideal, but for cryptography, drug discovery, AI, climate modeling, this quantum computing is used. So here I'll discuss about the representation, how the this qubits is being represented mathematically. So classical bit state is a set of 0 and 1, but the quantum state psi is a set of Kate 0 and Kate 1. So how to normalize this? We have magnitude squared alpha and magnitude squared beta that leads us to the 1. So to better understand, the block sphere has been devised, which is a graphical representation to represent this qubit, which says that a qubit states can be visualized as a point on a sphere where the poles represent 0. Both the poles, one is 0 and another is 1, that is represented as Kate 0 and Kate 1, and all other points in that sphere is the superpositions. What is superposition? Superposition is the probability of being 0 and 1 simultaneously. This is the two fundamental principle of quantum computing. First is superposition, which is principle of being probability of 0 and 1 simultaneously. So at a time, qubit exists in multiple states until it is observed or measured. So we have to measure or observe a particular position of that qubit to understand what is the current status. So how we can compare it with the real world analogy? When we spin a coin, and till the time it is in air, we cannot say that whether it will turn to head or tail, but it is both until it lands on the table or on the floor. So using the power of this superposition, quantum computers processes many possibilities at once, unlike classical computers. So another concept of quantum computing is entanglement. Entanglement means two states are connected. If we observe one state, the second state is connected. So this particular phenomena of quantum electrodynamics is referred by Albert Einstein as a spooky action at distance. So recently, the entangled pair of photons were kept apart for 1,400 kilometers, and it was observed and found that both are correlated. So how we can compare this phenomenon with real world analogy? When we roll a magic dice, if we see 6 in Delhi, we are pretty sure that same dice when rolled in Mumbai will show as 1. So this is called entanglement. Here I try to show how this qubit is very powerful to the level of exponential. 2 to the power n state is being represented simultaneously if n qubit system is used. But in classical computer, if n bit is there, then only one state at a time can be taken care of. So if 300 number of qubits quantum computer is made, then more than atoms in the universe can be measured at a time. So it is not possible with classical computer. And when it happens, then all the algorithm, this uh, all the encryption algorithm can be broken very easily. About the gates, here we have Hadamard gates, Poly X gate, and CNOT gate. Hadamard gate is usually used, and it is almost all the quantum algorithms base point. This is the basic gate of quantum circuits. poly X gate is used for correction and state preparation, and C NOT gate is also a core gate which is being used. So all these three gates can be clubbed simultaneously to achieve this quantum computing. As we all are aware that in classical computer, the NAND gate is a universal gate. So all the digital device which is available in this world uses NAND gates at its core. But there is a limitation of NAND gate. First, irreversible operations. The information cannot be reversed. Processing is sequential, and power and heat dissipation issue is always there. And the physical limit is limited by Moore's law, which says that if the chips can be increased with number of transistors, if it is doubled, the rate is getting halved. So there is a limitation of having a chip with the number of transistors in that. Again, growing circuit complexity and cost will always be there. Then advantage of quantum computing is we can have reversible operations, superposition, which I had just discussed, efficient for specific hard problems, for cryptography and machine learning. Entanglement is one of very useful mechanism or the feature of this quantum computing, which can be used to have very secure communication channels. And the exponential speed is always there. How this the value of the qubit can be measured. So this is really very tricky. When we measure the qubit, the value stored in that qubit, it destroys the quantum states. Suppose you want to measure a qubit, immediately it destroys. So you can read only once. So we have to have a mechanism. See, calculation will be very faster. All the algorithms can be created that can be achieved in very low time, but we have to have a mechanism to measure it, which does not exist right now. And decoherence. Decoherence means disturbance. It is very prone to losing its state with the interference of heat, vibration, electromagnetic noises. So we say that the states are extremely fragile. The state of quantum computing is very fragile. So these two algorithms are of very helpful for our NIC colleagues. I recommend to please go through these algorithms, and this is really very much helpful in our, and we can understand it very easily. This source algorithm is talking about breaking of all the cryptography. So it is having exponential time complexity if it is classical, but in quantum we have polynomial time complexity. So this source algorithm can be used to break RSA 2048 encryption in hours, which is being taken by millions of years by classical computer. So this algorithm drives urgency for post-quantum cryptography. We have to prepare ourselves for post-quantum cryptography. And another one is Grover's algorithm. So the complexity is normal if it is classical, but it gets speed up with quadratic using quantum computing. So searching 1 billion of records takes 500 million searches, comparisons. But when he uses Grover's algorithm, it takes only 31,000 plus operations. So you can think because we in NIC maintain very large databases, for some time when we query, when we try to extract the data out of database, it takes large amount of time, and sometimes we feel that it is really not feasible to uh, cull out the data from the database. Using Grove's algorithm, we can do it in fraction of seconds. So this is four of the applications of quantum computing. First is quantum simulation, which can be used for drug discovery, material design, and to simulate molecular and chemical reactions at quantum level. Optimization problem can be solved very easily. So non-deterministic polynomial hard problems can be solved exponentially faster. The traveling salesman's problem can also be solved in very easy way for this very complex problems. Quantum cryptography, QKD, it is really useful for us. Quantum key distribution, which will remain unbreakable. And post-quantum cryptography, we need to start working on that. Government and military secure communication, for this, it is useful, relevant for NIC's e-governance secure data channels. And for AI and data search, Grover's algorithm can be used, quantum machines learning. We have this quantum computing useful. So till now we understood that the very nature of this quantum is fragility. It is prone to change the state, which lead it to have very cooling condition, so that it does not get interfered by outer environment. So this same fragility had given an opportunity to the industry to start working on quantum sensors. Quantum systems are extremely fragile, so sensors need this level of fragility. So more the fragile nature, more the better level of quality of the sensor. Using this whole industry has started working on different type of sensors of very good that value or the sensing capability. And we believe that quantum sensors are low-hanging fruit, which can be achieved in very near future. Apart from that, we can have atomic clock, medical imaging, navigation system, gravimeter, drug discovery and defense, and intelligence. Quantum cryptography. So what this people who are into these adversaries of stealing our data work on the principle of harvest now, decrypt later. So they are trying to harvest our data, keeping in their safe custody and waiting for quantum computing, quantum cryptography, quantum algorithm to be in full swing, so that they can decrypt our data and use in that particular point of time. So we have to have very much proactive to keep our data in safe custody, so that they will, even if we think that this encryption mechanism is not prone to that is not vulnerable, but we have to think of the future when the quantum computing is in full fledged, and they will still they will decrypt our data and start using that. So this finance and banking industry, supply chain and logistics, and healthcare and pharma, these three industries are we can think of using quantum computing in these three industries. So now I'll talk about few of the tools, computing tools and platform for quantum computing. First is IBM Qiskit. This is open source. It provides SDK, which is based on Python. All the Python developers can start exploring using this toolkit. to build and run quantum circuit. What is quantum circuit? Quantum circuit is nothing but you can think of a program or set of instruction, quantum instructions to achieve a goal. So we can have, we can build and run this circuit on real IBM hardware. So they are providing 5 to 127 qubits processor. So recently one news has come last week only, 5 qubit quantum computer was set up in Kolkata. That was the third quantum computer in our country. So 5 qubit is, though it is very low, the processing speed will be very low, but we are achieving in that direction. We are moving forward in that direction. We can have a higher qubit processor available. So for Qiskit, we can, they have, the IBM is providing rich tutorial, textbook, Jupyter support is always there. Then Google is providing Circ. Again, it is open source. Design can be done. The circuit can be designed using this, can be run on Google's processors, Google's Sycamore processor. And Azure Quantum is also there. We can have hardware agnostic frameworks. All those can be used. So for that, we have to have foundational layer, simulator, because when we write, we have to run it. For that, simulator is required. So for that, we have Qiskit Terra, Qiskit Air, Qiskit Runtime. So any of these three can be used. What is the feature? How it is being used? We define the problem. Suppose we want to break any of the algorithm, RSA algorithm we want to break. So we can define the problem. We have to build a circuit. Then we can simulate locally using this and these three, one of the three simulator I had mentioned, and we can optimize, we can transpile, and we can submit to the IBM cloud. After the processing, we can analyze the result. All these things can be done. This is some snippet of Python program based Qiskit circuit. So here we have to import quantum circuit and simulator we have to import, and then we can write program. Any gate like Hadmard gate can be used, CNOT gate can be used, and how to measure, how to simulate, and how to count the output. That all activities can be done. So there are few challenges. The first challenge is extremely cooling condition is required. Coherence rate is very high. It is very prone to interference. All those processor we have, quantum computer we have having very limited qubit count, and the cost is also very high. On the top of everything, we have talent gap. So, but for this, we need to have physics, mathematics, computer science, and hardware engineering. All these type of disciplinary skills are required. But after this Qiskit and other Circ framework, all our NIC colleagues can start building some basic circuits. So I would like to mention over here that in India, Government of India has set up National Quantum Mission, NMQ, and the nodal ministry is Department of Science and Technology, and India has set the target that by year 2031, India will be placed in top 5 nations in quantum technology. And NIC can play a pivotal role in policy, infrastructure, and secure digital governance. And the budget allocated for these 5 years is 6,003 crore. So what all scopes are there for NIC? What is the strategic direction in quantum era? So we have to understand our current status and why we think that NIC must act now, because we are handling critical government data, and we understand that all the encryption mechanism placed today will be broken by quantum computers. So proactive preparedness is essential. How to move ahead? We can have awareness and capacity building program. Then we have to have industry industry and research collaboration. Then infrastructure and strategy is also required. Data security preparedness, we have to start from today itself, and securing NIC network. So at the end of this slide, I would like to reiterate that quantum does not mean faster CPU. It solves specific hard problems exponentially better and not everything. Security is now. Post-quantum cryptography migration is urgent. Data encrypted today can be broken later. India is investing. Already told that 6,003 crore have been allocated to the National Quantum Mission. NIC must align its roadmap accordingly. And recently, Ministry of Electronics and IT has funded CDAC to set up 5-qubit quantum computers. So today we have Qiskit, Circ, which is accessible. We can start experiencing, we can start learning the real quantum hardware in the cloud. So how governance is going to be impacted? Quantum will transform e-governance. We have to secure data, optimized system, and smarter decision. We have to take a smarter decision in this direction and learn continuously. We have to keep on learning. We have to have learning curve. So quantum revolution is not a question of if. It is not the question whether it is going to happen or not, but the question is it is when. So it is time to be prepared, and we all have to start dirtying our hand with the coding. And I'll request all my colleagues to start exploring quantum computing. We can have a discussion forum. We can have technology sharing session, more session like this, and we can take NIC to the direction with the quantum computing. So AI division is there. They are doing very good job. But if we can combine AI with the quantum, we can think in that direction. So keeping this as a food of thought to all of you, I'll take your leave with final words that quantum revolution is not a question of if, it's when. So it is time to be prepared. Thank you very much.